This is Jack Jackson, and we're going to continue here looking at Newton's method. In this video, we're going to look at some other types of situations where we can use Newton's method. Now, technically speaking, Newton's method is used to find when a graph crosses the x-axis, and it'll find, or at least approximate, the x-coordinate of that point. In other words, sometimes these are called zeros of the function, the x-coordinate of the x-intercepts. Okay? But we can also use it to do a couple other things. One thing we can use it to do is to solve where two graphs cross each other, if we manipulate it just a little bit, or equivalently use it to solve any equation with one variable. And let's see how we can do that. Well, if you've got two graphs, say one is y equals f of x, and another one is, say, y equals g of x, and you want to know where they cross each other, then you're asking, you're asking to find the x value, let's say, of the point where they cross, and maybe the y value as well. And what we know is that when they cross, those x and y values are the same. So we can set these equal to each other, and equivalently what we're doing is solving the equation f of x equals g of x. Or if you start with the equation f of x equals g of x, we're equivalently finding the x value where those two things are crossing. Now, solving that equation is equivalent to subtracting g of x from both sides and solving the equation f of x minus g of x equals 0. Or in other words, if you make a new function v of x equals f of x minus g of x, we're finding the zeros of v of x. That's what Newton's method applies to. So that's basically going to be our approach. So let's look at a couple of examples. Here is where f of x is x to the fourth and g of x is 4 to the x. And I've graphed these things here. And notice in this window we see a couple of places where they cross. Of course, we know something about these graphs already. 4 to the x is an exponential growth. It has an asymptote of the x-axis, y equals 0, on the left, and it increases concave up the whole way. X to the fourth comes down and then hits the origin and turns around and comes back up, so it's concave up the whole way with a local and global minimum at the origin. So we can look at where these things cross each other. Actually, they cross each other 3 times. You can see 2 of them here, but we know that eventually an exponential function is going to dominate. So eventually the blue graph has to be on the top. And if we zoom out a bit, we can see the other point of intersection here, and there's one right here where the blue ones, and then from there on out, the blue one actually dominates. The exponential is on the top from there on out. There's another place where they cross right in here, and another one, which was kind of hard to see on this picture, but it's right in here somewhere. We could see it better on this other picture. Okay, so we can think of it as finding the solutions to this equation, which are going to be just x values, or we can look at it as finding these points of intersection of these two graphs, which are the same x values, but then of course they each have a corresponding y value with them as well. And one of these is sort of an obvious solution. It may not be obvious to you at first, but once I say it, you'll go, oh yeah, that's obvious. And that's actually this furthest one out to the right. Look where it approximately is. It's about 4. What happens if you plug in x equals 4? You get 4 to the fourth equals 4 to the fourth. Certainly that's true, right? And of course 4 to the fourth, I believe, is 256. Okay? And so that gives us one of the points on the graph. Can't see it in this window here, but in this one down here, here it is, right about here where they cross. That's the point, 4, 256, right about where I got my cursor there, if you can see it. Okay, there's also another one that's sort of easy to find once you think about it a little bit. It's a right around 2 here. In fact, it's exactly 2. Plug in 2, you get 2 to the fourth equals 4 to the second. Those are both 16. So that point is 216. So if we're talking about solving the equation, we've got 2 solutions exactly. X equals 2 or x equals 4. If we're talking about finding the ordered pairs, we got 2 places where the graphs cross exactly. One is 4, 256, and the other one is 2, 16. But then there's this other place. We can see better in this picture. This point right here that's a negative value. And there's just one negative value here for x, positive for y, that makes this equation true but there's no way to find it algebraically. The techniques that we would normally use for an exponential function here by taking logarithms are not going to help us, because we'd still end up with at least a log x in here that we couldn't get by itself. Nor would the power function things. When we take like the fourth root of here, we still have this x in the numerator. So neither technique is going to work. In fact, there's not an algebraic technique for this. So the only thing we can do is do some sort of approximation technique like Newton's method. And so how are we going to do this? Well, we have to change the form, and we change the form by setting it equal to 0. And now we have this new function we'll call f of x, which is 4 to the x minus x to the 4th. And that's graphed here in purple. It touches the x-axis at 4 and at 2 and at this negative value right in here. Let's just get rid of the original functions. So let me say this first. Where the original functions cross each other is where this new function crosses the x-axis. So let's just zoom in a little bit different window and look at just that function, and you see, sure enough, there it is crossing at 4, at positive 2, and then somewhere in here around negative 0.7-ish. Looks like, looking at my scale here, negative point something anyway. So I'm going to take my initial guess to be negative 0.7. Now I'm just going to use the calculator to calculate the numerical derivative, so I don't have to bother with coming up with the formula, although it's pretty easy to do a formula for this one, for the derivative. So we could actually find the formula and put that in y2, or just use the numerical derivative. I took x and stored it as, took negative 0.7 and stored it as x, and then I did my Newton's method command here, which is x minus y1 of x, y1 is the original function, divided by y2, which is the derivative of the function we're looking for, at least approximately. And then we're going to store that back in x. And so then that says our x0 is negative 0.7. Here's our x1, x2, x3, x4. And x4 and x5 are the same. So we see that we have this approximated as far as we're going to be able to do so on the calculator. So Newton's method ended up generating an approximation of x is approximately negative 0.76664696. Now, if all we're doing is finding the solution to the equation, the original equation that we had right here, x to the 4th equals 4 to the x, we just need the x values, and we're done. And so the x values are x equals 4, x equals 2, or x is approximately that value we just came up with. However, if we want to find the ordered pairs of the intersection of the two graphs, the intersection of the red and blue graphs, so we got one here, and the one that's right over in here, better seen here, then we need to order pairs, so we need to take that x value, which is stored in x still, right, and then do either 4 to the x or x to the 4th. Either way, you get the same y value, and of course that's the point. It's the same x gives you the same y on both curves. And so now we know that those intersection points are 4, 256, 2, 16, and approximately that same x value, negative 0.7666. I think there's 3 6s, right? No, there's 4 6s. Yes, that's what I have. 4 6s, and then 4696. That one's missing a 6 there. That's the problem. There we go. And the corresponding y, as you saw right here, was 0.34547911638. Okay, so as far as my calculator can go, that's the best we can do at approximating that point. Now, once again, let me remind you that your designers of your calculator, they know a little calculus, and they know something about Newton's method. So they've actually built this process into the calculator. So here's how you do calculate an intersection of two graphs in the calculator. Is you put them in, one into y1 and one into y2. You do calc, which is second trace. Choose number 5, which is intersect, short for intersection. Identify the two curves. Use your up or down arrows to get on the curves and press enter. Provide initial guess and then enter and then do that. So let me see if I can do that on this one here. Okay, so I need x to the fourth and 4 to the x. And let's say, well, let's just do a zoom standard and start with that and see what happens. Can we see the point of intersection over here? Well, it's on the screen. Yeah, we can sort of see it. It's right in there. So what you do is you go second trace, which is calc. We want to choose number 5, which is intersect. So I can either arrow down and hit enter, or I could just press number 5 here. Now, you could have up to 10 graphs going at once. So it needs to know which 2 you need a paragraph. So there it is, Y1. So that's one we want. Hit enter. Y2, enter. If it's not the one we want, you can use the up or down arrows and notice it switches curves. Then it asks us for a guess. We seed it with the guess by getting close to it. And then basically it does the Newton's method stuff in the background, and sure enough comes back with both the x and the y values, which agree with what we just had. And it even takes those, and if we quit and just hit x, it will be that x value. And when we do alpha 1, which is y, that will be the y value. So if we ever need to use them again in later computations, we can. Now here's another question for you. How can we use Newton's method to approximate extrema of a function? Well, think about it a second. Extrema of a function, one place they can occur is when the derivative is equal to 0. So we're finding the zeros of the derivative. Now there are some other places extrema can occur. One thing can happen is at the endpoints of a function, or places where the derivative is undefined. And Newton's method is not going to help us at those places because the derivative needs to be actually defined to use, think about it, to use the way the Newton's method iterative process. So we can just find the formula for the derivative and approximate its zeros using Newton's method. Or if we have a calculator, we can apply Newton's method to the numerical derivative, the symmetric difference quotient. So here's one. Now this one we can actually do by hand pretty easily, but just for illustration, here we have f of x equals x plus 2 times x plus 3 times x minus 4. Okay. Now we can find the derivative, which is the derivative of the first times the other 2 plus the derivative of the second times the other 2 factors plus the derivative of the third factor times the other 2. That's sort of our triple product derivative. And here we could just do a little algebra, FOIL this out, and this one, so this gets x squared minus 12 plus 3x minus 4x is minus 1x. This here we get x squared, 2 times negative 4 is negative 8. We get 2x minus 4x is negative 2x. Here we get x squared plus 6, and we get 2x plus 3x is 5x. Combine like terms, we get 3x squared minus x minus 2x is minus 3x plus 5x is 2x. Negative 12 minus 8 is negative 20 plus 6. Wait a minute. Negative 12 plus negative 8 is negative 20 plus 6 is negative 14. That doesn't look right. And the derivative of that, which we're going to need, so we want to find when that's equal to 0. The derivative of that is 6x plus 2. Alright, so this is out of whack here. So let's see if we can fix that. Okay, so let me fix this a bit. Let me put in y1, I'm going to put the original function. Okay. Just go ahead and fix this. X minus 2, x plus 2. X plus 3, x minus 4, and the derivative we came up with was 3x squared plus 2x minus 14. Okay, and the derivative of that was 6x plus 2. Okay, and I'm not. Let's look at the, well, let's turn off the second derivative. Let's look at the graph of this. Let's just start with the zoom standard and see what happens. So there's the graph of the original, and there's the graph of the derivative. Let's do a couple other things. Let's make the graph of the derivative of the original darker, and let's change our window a little bit. Let's see, negative 25 to 25. Let's see if that makes it any better. Can't quite see the minimum there. Okay. So let's keep going with this a minute. Okay. A little bit. Change the window down a little bit further. How about negative 50? And if I want to do that, I better mark it off in 5. So let's see how that looks. Alright, that's looking pretty good. That's a pretty decent window. We can actually come in a little bit too on the outsides. We don't need to go as far out. How about just negative, how about negative 8 to 8? Just come in a little bit. Okay. So let's use that for our window. Okay, and let's correct our formulas. So this would be our corrected formulas here. And then let's again look at the graph. And this is going to have the graph of the original and the derivative. Okay. Now, what are we looking for here? We're looking for, originally we're looking for the extremum of the original one. Let's say this minimum right here. So we want to find this minimum. This minimum on the original function is going to occur when the derivative is 0, which looks like it's close to 2. So that would be a pretty good first guess. Okay. So let's see this with a first guess of 2. So take 2, store it as x. Actually, let me just clear everything out here. Okay, now 2, store as x. Now, what do we want to do? We want to do the Newton's method thing, which is take x minus the function we want to find the 0 of, which is actually in y2. Okay, so variables, y variables, function y2. Evaluate that at x. Divide it by the derivative of that function, which is in y3. Okay, so evaluate that at x, and then store our answer back in x. And we do this a few times until the number doesn't change, and now we have what we're looking for, which is the numerical approximation of the derivative. Okay. Get those to all fit nicely there. Line them up just a little bit. Okay. So there's our x value. So it looks like the extremum occurs at approximately 1.852479508. Now if we wanted to find this exactly, we would have to solve this quadratic equal to 0, which we could do with the quadratic formula. But this gives us one way to do it as an approximation. Okay, so one extremum, and that's actually a minimum. Okay, what's the corresponding y that goes with that? Well, once I have this, remember that's stored as x, right? So now I can just do y1, which is my original function, of that x value that we just have, and that'll be the corresponding y. Okay, so let's see what we got here. So the local minimum occurs, and x is that, and y equals negative 40.1459153. Okay, and we could find the, we can similarly approximate the coordinates of the local maximum. Okay, so let's look at another example. Approximate the maximum of the following function with the smallest x value. This has actually periodically, or I don't know if they're periodic, but it has a variety of different maxima here, probably infinitely many actually. But there's this first one that we're looking for, right? Right in here you can see the graph. So f of x equals 2 ln of x times sine of x. So we graphed the original function in y1. We're going to need its derivative, y2, to see where it crosses the x-axis. And the derivative of that we're going to need, we always need one extra derivative to do Newton's method. If you're trying to find the 0, 1 function, you need its derivative. So to find extrema, we want the derivative to be 0, which means we're going to need to go as far as the second derivative. So here you can see the window I have and the functions I have. And this time I'm going to try to avoid actually finding a formula for a derivative and actually just use the built-in stuff in the calculator for numerical derivative. So it looks like the point we're using, this scale is going up by 1 on x's. Looks like there's 1, there's 2. Looks like it's pretty close to 2. So I'm going to seed it with 2 for my first guess. X minus, well, the function I want to find the derivative of is in find the 0 of is in y2. So it's y2 of x divided by its derivative, which is y3 of x, and stored as x. Execute that 2 or 3 times here, and we see that we get an x value. And then take y1 of that x value, and we get the corresponding y value, and we found at least approximately the x and y coordinates of that maximum point on the original graph. Now, this process, again, is built in the TI-84. The designers of the calculator know this technique, so they're going to build it. They built this in. And the way you use the built-in technique is basically like this. You press calc maximum. Now calculate is second trace. Choose number 4, maximum. It's going to ask you for a left bound. Use your left and right, first of all, up and down arrows to make sure you're on the right curve. Then left or right to get to the left of this point of maximum here. Hit enter. Move over to the right side. Press enter for a right bound. Move over as close as you can get to the maximum. Hit enter for your guess. That's our initial number that we're seeding Newton's method with. And then that produces a maximum right there. How about approximating inflection points? Okay, So we should be able to use a similar technique to approximate inflection points. Now, if we look back at this graph, it looks like there's an inflection point in the original graph somewhere close to 1, x equals 1. So right in there, if you can see my cursor moving around down here at the bottom, see that graph? Somewhere around 1 in here, there's an inflection point. Let's see if we can approximate that. Now, if we want the inflection point to find that, that's when the second derivative is 0, which means we're going to have to go as far as the third derivative. So here we're going to try to do this by, remember, y1 is the original function, y2 is the derivative of y1, the first derivative, y3 is the derivative of y2, the second derivative, y3 is the derivative of y2, so that's the third derivative, first, second, third derivative, right? And we need a third derivative to work with this. But the problem is, so we store 1 as x and we try to execute this, and then we get this error message, illegal nest. Now what's happening here is there's too many operations inside of operations, nested operations, because what this is doing, we're asking it to work with the fourth y4, which is a numerical derivative of y3, which is a numerical derivative of y2. So you have a numerical derivative that's a symmetric difference quotient of a symmetric difference quotient of a symmetric difference quotient. And remember, each symmetric difference quotient requires you to do other functions. So it's just too much for the calculator to handle. So it won't do this. Okay. So, well, are we stuck? Sort of. If we don't find a formula for a derivative, yeah, we're stuck. So that's why the calculator does not have a built-in inflection point calculator. Okay, otherwise they could just build this in pretty easily. However, all we need to do is just take one derivative and then we can actually figure this out. So if we could just replace one of these, say y2, with the actual formula for the derivative, not just a numerical derivative, then the calculator can handle a couple layers of these, but not 3. So if we could just actually replace that with the formula, then we can go ahead and do what we plan to do here, just like this. So let's go back and calculate the derivative. Okay, so our original function is 2 natural log of x times sine of x. So I pulled the 2 out front. First part is log of x times derivative of sine x is cosine x plus sine of x times derivative of log x, 1 over x. And I basically just entered it just like that for y2, replacing the numerical derivative. Now when I go back to store 1 as x and try to do this x minus y3 of x divided by y4 of x store as x and execute that with Newton's method, it does work. And in fact, I get out an x value and I could do y1 of that x to get the y value. And now I've found that inflection point, at least approximately, the x and y coordinates. You can see them there. X is about 1.101436925 and y is approximately 0.172334878. So as far as my calculator goes, that will do that. And by the way, notice that there is not a built-in inflection point calculator, so you'll need to do something like this. Of course, another way to do it would be, remember that an inflection point occurs on the original function when the derivative is at a maximum or minimum. So we could actually compute the formula for the derivative, like we did here, and then graph it, and then do a calc maximum or calc minimum as appropriate on that graph, and that will be what we need. So if we look back at the graph, I think I had one right here. Yeah, here's one where you can see the derivative, and this one where that derivative is at a maximum is where the original function is at an inflection point. And there's another one over here. See where the derivative is at a negative. The original function has an inflection point there as well. And so, of course, we have to calculate this for each one of those if we want to find them approximately. Okay, so I think, okay, so that's going to be the end of what I think I'm going to do on Newton's method. So why do we do this? Well, we did this for a couple of reasons. Number one, I want you to get an idea of what's going on with the calculator. It's a slick little idea, and it really just leverages what we know about derivatives to be able to come up with these approximations. And also, of course, there's the people who push the buttons on the calculator, and then the people who design what goes in, what happens when you do push those buttons. And hopefully some of you guys will be maybe some of those guys that that actually get into these things and understand how these things work inside calculators and computers, and might someday actually program some algorithms like this, or maybe other algorithms, into calculators or computers. So definitely something to think about. But anyway, they've come up, Newton and other mathematicians came up with this nice method, and it works very, very nicely for us. And much of it's built into the calculators already.